Working 11.6, directional derivative in the gradient vector. Going to be working problem 1 to start here. So we're given here f of x, y, equals y e to the negative x. So that's some surface sitting there. I'm given a point, 0, 4. I'm given an angle, theta equals 2 pi over 3. And I'm asked to find the directional derivative of f at the given point in the direction of the indicated angle. Okay. All right, so let me draw, first of all, a two-dimensional picture of the domain. Okay, here's the domain of this function of two variables. And I'm looking at the point 0, 4, which is 1, 2, 3, 4. Okay, and I'm pointing at a direction of 2 pi over 3. So remember back from, unit circle, pi over 3, 60 degrees, 2 pi over 3 is 120, and then 3 pi over 3 is just pi. So we're pointing in this direction, but we're at this point. So it's going to be like something like this. Okay. So imagine now that this is on the ground, okay, and we have a surface above this. So I'm going to try and draw a picture of that. I won't draw pictures for this whole thing. This is just first example to get us started here. So I have my axes here. This is x, this is y, this is z. I've come out here on the y-axis 4 units, 1, 2, 3, 4, and I'm pointing in this direction here, so that corresponds to something like that. And then above this, or below, it depends on the function, but we have this surface sitting above this, right? And if you plug that point up into the surface, you get some point on the surface. And what we're trying to figure out is if we were to go and start moving in the same direction as this vector, okay? If we were to move in that direction, would we be going up or would we be going down, and how much would we be going up by or down by? So that would be like a slope of a tangent line. So this is what the whole directional derivative is about. It's about changing our direction so that we're not just parallel to the x-axis or parallel to the y-axis, which is what the partial derivatives were, partial with respect to x and partial with respect to y. Here, now we don't have to do that. We can point in any direction we want. So to do this, we will be using a formula that was given in class, and I'll reference this. I'll tell you where it is. There we go. Okay, so the notation for this is that the directional derivative in the direction of u is equal to, of the function f of x, y, of the function f of x, y is equal to a times the partial derivative of f with respect to x plus b times the partial derivative of f with respect to y. Now, A and B come from the vector u. So u is a vector, has two components, A and B, and this must be a unit vector. So the vector u points in the direction that we want to point in, but we got to make sure it's a unit vector. So this vector right here, this red one right now, I'm not going to call that vector u because I don't know if it's a unit vector. So let's just figure out what this vector is first. if we can write this in some form. So let's imagine, let's move that vector down like this, because it's a vector we can. We know that this angle here, right, is 2 pi over 3. And so if we were to just go to the unit circle, go back to that picture, and go back to that vector. I guess I should have drawn it in blue. Let me do that. Here's our unit circle. Here's our vector. It corresponds to a point on the unit circle. That point is -1/2 root 3 over 2. And so if I look at that point as a vector instead, that goes from the origin to that point, this vector that points in the same direction as this one does. And so the only question is whether or not this has unit length, whether or not it has a length of 1. Well, it came off the unit circle, so obviously it should have a length of 1. But we could double check it real quick. Take its magnitude, square root, just square each one. So square that, that's 1/4, plus square that, square top you get 3, bottom you get 4. Add them together, you get 4/4, that's 1. So that is a unit vector. So for this problem, we have to use the angle to come up with our vector, which is going to be our u. So u in this problem will be the vector -1/2 root 3 over 2. And so that's A, and that's B. So the next thing I'm going to do is use this formula to go ahead and get my partials. I'm going to get my partials now, okay, and then I'll put it all together. So what is the partial of this function with respect to x? Well, here's the function. We treat y as a constant here, so y is just coming along for the ride. The derivative of e to the negative x is itself times -1 because of chain rule, so I'm going to put that out in front, -y e to the negative x. And then the partial of f with respect to y, this time x is a constant, which means this is a constant, and then derivative of y is just 1, so we get e to the negative x. Therefore, here's what we have. The directional derivative in the direction of the vector u of our function f of x, y should be equal to a, which was -1/2, times the partial derivative of f with respect to x, which was this, -y e to the negative x, plus, I'm out of room, b, which is root 3 over 2, and then times partial of f with respect to y, which was e to the negative x. Now this is going to get this, when we use this formula, this is going to give us a number, right? If I plug in an x and a y, I'm going to get a number. That number is going to represent that slope of that tangent line up on that surface. So let's go ahead and do that now. We're going to ask to find the slope of tangent line at a specific point. So let's go ahead and plug in that point. The point that we were given was the point 0,4. So the directional derivative in the direction of u of the function at 0,4 will be equal to, let's see, when I put these two together, this negative and negative become positive, so it won't matter. So I'm going to have 1/2, and then y is 4, so 1/2 4, and then e to the -0, but e to the -0 is still e to the 0. Then I have plus root 3 over 2 times e to the, again, -0 is still 0. So we get 1/2 of 4 is 2, e to 0 is 1, so it's just 2, plus e to 0 is 1, so root 3 over 2. And I mean, that's it. That's your exact answer. You could get a decimal. I could get a common denominator if I wanted to. There's a lot of things I could do, but that's the exact answer. Now let me see if they actually give you a, see if the solutions have the decimal. No, they just leave it as an exact answer. So this is fine, just like this. All right, let's move on. Let's do number 2. This is a really good marker, but it's hard to erase if you let it dry for a little bit. I realized finally that the black markers that they are buying for us here are the low odor ones, so they don't smell real bad, but they don't write real good and they don't last very long. These blue ones, though, are not the low odor. Well, yeah, they smell good. So they have a better, they last longer and they're darker, so it's good. Hopefully the video comes out good. All right, so how about number 2? I'll let you do number 2 since it's very similar to number 1. Let's look at, on the next one, I'll do number 4 and number 6. So number 4, so I'll do some evens here. Number 4, they give you a function of 2 variables, f of x, y equals y squared over x. They give you a point, 1, 2. They give you a direction, or they give you a vector u, which is the vector, this is weird looking, I'm going to convert it. It's 1/3 times 2i, so that's just 2/3. And then 1/3 times root 5, so this is root 5 over 3. So I'm just converting it from their form. They gave you 1/3 2i hat plus root 5 j hat, and then I just turned this into the vector root 5, and then just came through with the 1/3. So I mean, yeah, with the 1/3. So that's it. So we're asked to find a couple of things on this. So let's understand what we want here. Part A, find the gradient of f. B, evaluate gradient, I'm just going to put grad, at P, at the point P. And then C, it says find rate of change of f at P in the direction of u. So find basically the derivative in the direction of u of f at P. Okay. All right, so let's take a look at this. Part A, what is the gradient of f? Well, the gradient of f, we write del f, and it's equal to, in this case, since it's only 2 variables, it's a vector. It has 2 components to it. The first component is the partial of f with respect to x. The second is the partial of f with respect to y. So this is going to be equal to, all right, what is the partial of f with respect to x? Well, rewrite this as y squared times 1 over x, and then y is a constant. So derivative of 1 over x is negative x to the negative 2, so negative 1 over x squared. So that just turns into negative y squared over x squared. And then the partial with respect to y, x is a constant, so that's a constant derivative. Y squared is 2y, so we get 2y over x. So that's your gradient. Part B says evaluate the gradient of the function at the point. The point was given to me to be 1, 2. Okay, so I'm just going to replace x with 1 and y with 2 in this. I'm going to get a vector. Okay, so the vector that I get is, let's see, 1, 2 goes in here, so negative 4 over 1, so negative 4, and then 2 in here, so 4 over 1, we get 4 here. So that's the gradient at the point. They just want the gradient, right? Not the magnitude. Okay. Okay, so that's B. And then for part C, it wants to find the rate of change of f in the direction of u at the point P. So this is a directional derivative, which means that we have to make sure that u here is a unit vector. Very important. Is this u a unit vector? So here's the u they gave me. Let me just check that this is a unit vector. I do that by just taking its magnitude. So what is the magnitude of u? It's going to be equal to the square root of this squared, which is 4/9, plus this squared, which is 5/9, and that is 9/9, so 1, so root 1, that's 1, let's check. Okay, so it is a unit vector, so we can go straight to the formula. The formula is that the directional derivative in the direction of u of f at xy will be equal to a, which is 2/3, times the partial derivative of f with respect to x, which we had just a second ago. That was negative y squared over x squared. And then plus b, which for us is root 5 over 3. And then the partial of f with respect to y, which we said was 2y over x. So that is the rate of change of the function in the direction of u at the point xy. So now I just need to plug in 1 and 2. So directional derivative of f at 1, 2 will be equal to, well, we already did this computation. I mean, notice right in here that this piece and this piece, that's the gradient, right? So I just scale it, right? 2/3 times, let's see, this first one was, what was it, negative 4, and then plus root 5 over 3 times this one was 4. So we get negative 8/3 plus 4 root 5 over 3. So negative 8 plus 4 root 5, all of it over 3. And then, of course, that you could get some decimal answer for that. Now, what's worth keeping in mind here is that this, it's like if we were up here on the surface of the function, this is one of the main points of this whole section. We're sitting here at this point, and if we point in this direction, so imagine on the ground, you know, somewhere on the ground here, I'll just put my axes here. Somewhere on the ground, I'm pointing in some direction, let's say that's you, okay? Then up here, I'm pointing in that direction. If I walk out in that direction, this is what's going to happen. This is my rate of change. What is that number? Let's see, I'm going to get my calculator. I'm just going to figure out what it is real quick as a decimal. This is keep messing up. This is 0.314 approximately, okay? So that means that if I were to be up on that surface, pointing out in the direction of u, that I would actually be going up, and this would be the slope, right? Up because it's positive. And I'd be going up, you know, my rise over run is 0.314. So I'm not going, it's not real steep, but I am going up. Now, the key, and the reason why I'm bringing this up, and the problem doesn't ask this, is that if I'm standing at this point, the steepest ascent that I could have is actually the direction, not this direction, but the direction of the gradient vector. Now, the gradient vector we found, right? It was, the gradient vector at that point was the vector negative 4, 4. So That's some other direction. It's not this one, okay? So I don't know where it is. I'm pointing in some other direction. That's the gradient of f. And if I point in that direction, I'm going to go somewhere over here. And that's guaranteed to be the steepest. And the actual value of that slope is just the magnitude of this vector. I just take the magnitude of it. So if I take the magnitude of that, you get square root 16 plus 16, which is root 32, which is definitely bigger than 0.314. 32 square root is 5.66 approximately. So standing at this point, if you go and you look around and you're trying to figure out where to go to get the steepest descent, I know I keep saying this over and over, but it's so important, trying to figure out which direction you should go. Well, you should point in the direction of the gradient vector. So you look down on the ground, you figure out where that vector is in two-dimensional space, and you follow that path, okay? Follow that path, and when you do that, you will have the steepest descent, and here's what it is. It's going to be a slope of 5.66. Now, as soon as you move to a different point, now everything changes, and you have a new gradient vector and a new direction and all that stuff. So remember, this is just handling what's happening at an instant in time, or an instant on the surface, it's not like a general answer that works for any point. So that was only for the point 1, 2 that all this information was correct. All right, let's see. Think you can handle the rest? I'm going to see. Just a little concerned because 6 has 3 variables, but it's the same thing. I haven't done one like that. Let me do 6. So 6, now you have a function of 3 variables, which means the domain is 3-dimensional, the output's in 1 dimension, and we need 4 dimensions to see it, so we can't really see it. This is y squared e to the x, y, z. The point that they give you is the point 0, 1, -1. And u, which, do they tell you it's a unit vector? No, they don't tell you it's unit. They kind of make you think it is by putting u out there. So you think unit, u for unit, but we're always going to check these to make sure they're unit vectors. All right, same directions as the previous one. So first thing I'm going to do is drink a little bit of coffee. Much better. All right, so first thing I'm going to do is find the gradient vector. Yeah, so the gradient of f, in this case, because it is 3 variables, partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. So 3 components to this vector, which will be for me, okay, if x is our variable, y and z are constants, then I can ignore that and bring it with me. Derivative of e to anything is itself. And then times the derivative of up here with respect to x. So these 2 are constants. Derivative of x is 1, so I get yz. Nice. Then the partial derivative with respect to y. So y is a constant. Notice I have y here and here, and I have a product, so I'm going to do product rule. So it's going to be, you know what, I'm going to run out of room. So let me do this. Let me bring this over here. This answer, I'm going to clean it up and bring that y together right here. So y cubed, bring the z out in front, z, e to the x, y, z. And then now let me do that partial with respect to y. So product rule right there. Derivative of y squared is 2y, e to the x, y, z, plus now derivative of e to the x, y, z with respect to y is itself, but then times derivative up here, which is going to be xz. I'm going to put that out front, xz, e to the x, y, z. but then times finishing off the product rule, y squared. And I think just for ease, I'm going to move that y squared over here. So I will have y squared z e to the x y z. And then finally, the partial derivative of this with respect to z, it's pretty much like the first one was. The y squared is just going to come along for the ride. When I take the derivative of this, I'm going to get itself, and then derivative of the top with respect to z, which is xy. So I'm actually going to have an x and a y pop out, which will give me xy cubed e to the xyz. All right, so that should be the gradient vector. I'm just double checking everything here. Okay. All right, so now we want to know the gradient at the point 0, 1, -1, and that's just going to be a vector. Plug in 0 for x, y is 1, z is -1. So here we get 1 cubed, we get 1 times z is -1, so -1. And e to the, well, if x is 0, then this is going to be just 1. So I'll just put e to the 0 here. 2 times y is going to be 2 times 1, and then e to the 0 again. Plus, and then here, x is 0, right? So this is all gone. And then over here, x is 0 also. So that. So all I get is the vector, let's see, this is -1. This is 2, and this is 0. There you go. The last thing is to find the directional derivative in the direction of u for this function. So I'm still going to use the gradient, all right? So one thing I could do is I could just take that the directional derivative, I could use this. You know, I just erased u. The directional derivative of u of the function f of x, y, z, all right, should be equal to the gradient of f dotted with u. All right, so it's this gradient vector, all right, dotted with the u vector, which I took the u off of here. I need to rewrite the darn thing. It was, oh, wait a minute. You know what? I wrote the wrong u down there. I'm glad I erased it. I was looking at number 5 for the u. The u is actually 3/13, 4/13, and 12/13. And find the magnitude of that. Just to double check it, the magnitude of u is 1. So it is a unit vector. So all I'm going to do is take a, which is this, in front of the partial of f with respect to x of x, y, z, plus b, which is this one, times partial of f with respect to y of x, y, z, and then plus c, which is this one, times the partial of f with respect to z of x, y, z. So if you were to take this, this is the vector a, b, c. This is the vector partial x, partial y, partial z. If you dot these, it's this times this, this times this, this times this, which is exactly what I have written down here. So I'm going to take a, which is 3/13, times this piece, y cubed z e to the xyz, okay, that's this, plus b, which is 4/13 times this piece, 2y e to the xyz plus xy squared z e to the xyz. Close that off. And then finally plus c, so plus 12/13 times this last piece, so xy cubed e to the xyz. I know that that's all crammed in there, but let me take this out of here. I just needed it for reference. Okay, there we go. All right, now let's just figure out what happens with the direction of f at the point 0, 1, -1. And this is going to be super easy because we already know what all these pieces are. Like I already know what this is, I already know what this is, and I already know what this is when I plug in 0, -1, 1, because we did that right here. So we know that this one is going to be -1, we know this is going to be 2, we know this is going to be 0. So if we know that, then the directional derivative of the function in the direction of u at the point 0, I just forgot, 0, 1, -1 is equal to 3/13 times -1 plus 4/13 times 2 plus 12/13 times 0, which is -3/13 plus 8/13 plus 0, which is 5/13. Okay, now let's discuss this one a little bit. This is much harder than to visualize. What we have is the domain of our function, all right? The domain of f is in three-dimensional space. And we're looking at this point 0, 1, -1. So here's x, here's y, here's z. We go 0, 1, and then down 1. So we're here in three-dimensional space. That's our point, 0, 1, -1. And we're pointing in the direction of this vector. So we are actually, it's a three-dimensional vector, so we are pointing somewhere in three-dimensional space. I'm exaggerating it, okay? And it's not straight up. Could be in any direction. So it's pointing in some direction in three-dimensional space. And if I were to start moving this point along in the direction of this vector, that point, remember, is being plugged into some function that we can't even see. So as I move this point around, the function's value is changing. It's not a surface, it's just something that's changing. If I go in this direction, then what I can tell you is that the function that I can't see is increasing because the directional derivative is positive. And the rate at which it's increasing is 5/13. So we no longer have the idea of standing on a surface and going out and going up or down. It's just that in this function, as I move in the domain in this direction, the function's values are increasing. Now, if I were to follow the gradient vector, now the gradient vector was the vector -1, 2, 0. If I actually stand at this point and go in the direction of this, right, which is some other direction, then what I can tell you is if I start moving in that direction, the function itself that I can't see will be increasing at its highest rate. And if I wanted to know exactly how fast it was increasing, I would just take the magnitude of this. So let's do that. Magnitude of that, square root 1 plus 4 plus 0, it's root 5. Notice root 5 is bigger than that. And that's because root 5 is the biggest increase you're ever going to get when you're standing at that point. That's the biggest increase, and you have to move in this direction in order for that to happen. All right, I hope that makes sense. It's hard to visualize that. We're doing on time. We got it going okay. Okay, let's do number 8. So for number 8, we have a function of 2 variables. It's actually a rational function. X over x squared plus y squared. We're given a point again, 1, 2. We're given a vector v, which is the vector 3, 5. And we're asked to find the directional derivative of the function at the given point in the direction of v. So I want the directional vector in the direction of v of the function f of x, y. But at this point. Well, we have a formula for this. But I need to make sure that v is a unit vector. And let me check it. What's the magnitude of v? Square root of 9 plus 25, which is 6. No, that's not 6. That's root 34, but it's not 1, right? So that's not a unit vector. It's not a unit vector. So how do I make that a unit vector? I need it to be a unit vector, but I want it to point in the same direction. Well, I just take that v, I divide it by its own length, and that will be a unit vector for sure. So 3 divided by its own length, 5 divided by its own length. That is what I can call u. That's my unit vector that's in the same direction as that one. And then what I'll do is I'll say, okay, they tried to trick me and they tried to use v. No, I'm going to use u. And now I can apply the formula. So the formula will be the gradient of f dotted with u, which is equal to, well, let's do the gradient of f. Ooh, we have to find some partials here. I might need some work for that. But u is easy, because u is just this vector. This is a, this is b. Okay, let me do some partials. I think I'll do them right here. I'll save this point, the point 1, 2. Okay, so what is the partial of f with respect to x? Well, I have quotient. I have to do a quotient rule because x appears both in the numerator and denominator. So derivative of the top, 1 times the bottom, x squared plus y squared, minus the derivative of the bottom with respect to x is 2x, times the top, all over the bottom squared. Which is x squared plus y squared minus 2x squared all over x squared plus y squared squared. Which is y squared minus x squared over x squared plus y squared squared. Okay, that's my partial derivative with respect to x. Now, how about my partial derivative with respect to y? I'll do that here. This time I don't need quotient rule. I guess I could. You know, let me do this to make this derivative easier. I'm just take the bottom and bring it up. So watch like this. So leave that x that was there, but then I'm going to bring the x squared plus y squared. I'm going to bring it up, so -1. When when I take derivative of this with respect to y, I can bring the x along for the ride and then just do a chain rule on this. So -1 comes out, make it -2, and then go inside. So the x is going to stay there. The -1 dropped out. We have x squared plus y squared to the -2. Then the derivative of what's inside with respect to y, which is 2y. And now I'll just drop everything back down. I'll leave -x in the 2y upstairs, -2xy over, this dropped x squared plus y squared, that quantity squared. So there's your partial with respect to y. All right, so this will be the gradient of f dot, we know what this formula turns out to be. I think I'm going to write it down first. It's a partial of f with respect to x at xy plus b times partial of f with respect to y at xy. It's our formula when we dot those two, which for us a is 3 root 34 times the partial of f with respect to x, which was y squared minus x squared over x squared plus y squared, quantity squared, plus b, which is 5 over root 34 times partial of f with respect to y, which was -2xy over x squared plus y squared, quantity squared. All right, there it is. That is the directional derivative. Now I need to do it at that point. So now I'm going to plug some values in. So the directional derivative in the direction of u of the function at the point 1, 2 is equal to, so what happens if I plug in 2 for y and 1 for x? So 3 over root 34. And then, let's see, this is 2 squared 4 minus 1, that's 3 on top, over 1 squared plus 2 squared, that's 5, and then squared, so 25. Okay, plus 5 over root 34 again. And then this is -2 times 1 times 2, so -4 over, we already said that was 25. So we get, see, multiplying these and these, we get 9 over 25 root 34 plus multiplying these, -20 over 25 root 34, which is -11 over 25 root 34. So we actually have a negative directional derivative. So if we go in that direction, we're going to be going down. Which one was this one? This was number 8. Okay, so let's see. If that's number 8, I'm going to let you try and handle 7, 9, 10, 11. 11 might be a little ugly because you've got function of 3 variables. I think 13 and 14 you can do. I'm just going to tell you be careful on those because they're giving you a point. So you have to come up with a unit vector on 13 and 14. Okay, so let's look at number 16. Time, we got 45, okay. 16. F of st, so they decide to use 2 different variables just to have fun. T e to the st, you have a point that's given 0, 2. You're asked in this problem to find the maximum rate of change of the function at the given point, and then what direction it occurs in. So this is a function of two variables, so we have, the domain is on the ground. We go out to the point 0, 2, and up here above is some surface. We think it's above. There's a point. Question is, what direction do I need to point in, right? So on the ground, what direction do I need to point in? Those are questions. What direction do I need to point in order to, up here, be going up the most, the maximum rate of change, to get the maximum rate of change up here? Well, that's easy. That's just the gradient vector is the direction, and the magnitude of the gradient vector is the actual maximum rate of change. So I just need the gradient of f first, which is some partials here, partial with respect to s and partial with respect to t. And so I take the partial with respect to s first. T is a constant, so I get, cover that up, derivative e to the st is itself, then derivative of st is just t, so t is going to pop out. I already had a t, so t squared e to the st. And then partial with respect to t, product rule. So derivative of t is 1 times e to the st, plus derivative e to the st with respect to t would be just s e to the st, but then finish off product rule, so times t. That's your gradient vector. If I find the gradient vector at the specific point, then I plug in 0 for s, be careful. E to the 0 is 1, and then t, I plug in 2, so t squared is 4. 4 times 1 is 4, so I get 4. E to the, again, 0, that's going to be 1. And then over here, remember, s is 0, so it's going to kill everything else off, so I just get 1. That is the direction I should point in order to get the maximum rate of change. That's it right there. Now, what's the maximum rate of change? I just take the magnitude of the gradient vector at 0, 2, and that's just square root of 16 plus 1, so root 17. Root 17, whatever that is. Okay. That is number 16. So I think with that, you can probably do, 15 and 17 and 18 yourself. I think 20 and 21 are good thinking problems. I'll talk about 20. Find the directions, plural, in which the directional derivative of this function at this point have the value 1. So really what you're doing there is you're trying to find a formula for the directional derivative at that point, and you're setting it equal to 1 and then trying to solve an equation. See if you can figure that out. 21 is find all points in which the direction of fastest change of this function is the vector I hat plus j hat, which is just 1, 1. Again, that one I want you to think through. I don't want to give that away. All right, let's get on to 31 through 30. I don't know what I did, 36 maybe. I'm just going to do one of these. So why don't I do 34? I'll do 34. Find the equation of the tangent plane and the normal line of the given surface at the specified points. So how much time do I have on this camera? I've got about 10 minutes and this video is going to cut off. So I think I can do this one problem in 10 minutes. All right, so find the equation of the tangent plane and the equation of the normal line, and we're given xy plus yz plus zx equals 5 at the point 1, 2, 1. All right, so the big difference between this and what we did in the past with the equations of tangent planes is that this equation right here cannot be solved easily for z. I mean, you could actually do this one for z, but we're trying to come up with a formula where we don't actually have to go through and solve for z. So what we do is we make sure we get everything to one side, except we can leave constants over here. And this is going to be what we call capital F. And then what we have is our point over here. This is what's going to be called x naught, y naught, z naught. And we have a formula for the equation of the plane. Remember, the general equation of a plane is x minus x naught plus, sorry, did I say x? A times x minus x naught, b times y minus y naught, c times z minus z naught equals 0. And the big result of this section in terms of tangent plane is that this a, b, and c can be found for finding the tangent plane of a surface by using partials. So this is the partial of capital F with respect to x at the point x naught, y naught, z naught. This is the partial of capital F with respect to y at the point x naught, y naught, z naught. And this is the partial with respect to z at x naught, y naught, z naught. So I need to figure out what those numbers are, and then I'll have my equation of my plane. So this will be pretty straightforward. Let's first find the partial of f with respect to x. Let's do that first. So with respect to x, it's y, 0, and z. So y plus z. Partial with respect to y, I get x plus z, 0. X plus z. Partial of f with respect to z, 0, y plus x. Y plus x. All right, so now let's go over here and let's plug in, for that partial with respect to x, let's plug in x naught, y naught, z naught. So let's plug in these values in here. So I think I'll do that right here. What is fx at the point 1, 2, 1? Well, that's just 2, and 2 plus 1 is 3. Partial of f with respect to y at 1, 2, 1 is plugging in 1 here for x and 1 here for z, I get 2. And then partial of f with respect to z at 1, 2, 1 is y, let's see, is 2, and plus 1 is 3 again. So now I can come back over to my equation for my plane. I know what these pieces are. I'm ready to go. So I have 3, x minus x naught was 1, plus 2, y minus y naught was 2, plus 3, z minus z naught was 1, equals 0. And let's clean this up. 3x minus 3 plus 2y minus 4 plus 3z minus 3 equals 0. 3x plus 2y plus 3z, let's see, negative 3, negative 4, negative 7, negative 10. Bring it to the other side, equals 10. Okay, that is the equation of the plane that is tangent to that surface. So it should be tangent to that surface at that point. Now they want the equation of the normal line. This is actually going to require very little work. So I'm not sure what this surface looks like, okay? We could graph it, and let's just imagine that we have some surface here three-dimensionally. Okay, it's just some surface. And what we did is we went to this point, which was on the surface, and we found the equation of the tangent plane which touches that surface. That's the equation. What we want now is the equation of the normal line through that point. So what you want to imagine here is that if this is the plane that's touching my surface tangent, right? It's tangent to my surface. Then here's that point. That point's right here. What I want is the equation of the line that comes out of the plane through that point that is normal. So it is actually perpendicular to my plane. Well, that's going to be so easy to do because first of all, what do we need for the equation of a line, vector equation of a line? We need a point and we need a direction vector, v. Well, I have a point, that's good. And a direction vector, well, how about we just use the normal vector of the plane? That would work. So that's all it is. My normal line, the vector equation of my normal line, I'm going to call it r of t, will be equal to r naught plus tv. R naught is any point on the line, but specifically we want this one. So 1, 2, 1 written as a vector plus t times the direction vector. The direction vector, like we just said, we can use the normal vector of the plane. The normal vector comes from your ABC. So we just use 3, 2, 3. And then put this together, you get 1 plus 3t, 2 plus 2t, 1 plus 3t, and that's it. T is a real number, that'll draw the whole line. So that line should punch through your plane, through that point, and run perpendicular to your plane. Gonna just double check that, make sure I did that right. I didn't make any little mistakes. Which one was that? 34. Looking good. Okay, so I'll see if you can handle the others. I got lucky. The partial derivatives for this one were pretty simple. So hopefully yours won't be that bad. All right, that should be perfect as far as time. Get this all in one video. Awesome.